Okay, ladies and gentlemen, good afternoon to you guys. Is it afternoon? I think. Anyway, let me get comfortable here and let's talk about what we're going to do now with this here. So ladies and gentlemen, I'm going to try to get your stuff graded this weekend. Okay? I'm going to try to yeah, let's take a look here what's going on, all right? You guys okay with that? Now, remember, I'm going to say recall, I gave you guys a statement here about the harmonic series, right? The very famous harmonic series diverges. This is a statement that it diverges here, right? The harmonic series diverges. Now, the proof in your book is a great proof. However, it's pretty much involved. And let's actually write down what that harmonic series actually is. 1 plus 1/2 plus 1/3. This goes on forever. Okay, that infinite sum blows up. Now, what I do is I wait, ladies and gentlemen, to this section to go through this. You say, what is the section? Well, this is called the integral test. Now, remember I said to you, we're going to have a whole bunch of tests now for convergence now? So the integral test is a test about what? Convergence. It's a test over convergence. So let me give you guys the integral test, okay? Now remember, here we're talking about a series where an is going to equal what? Fn. Okay, so we already know, okay, this is an is Fn. So here's kind of what you want to do. Here's the assumptions here, right? You want to let F be continuous and positive. Okay, so your function has to be continuous. It has to be positive. F needs to be decreasing on the infinite interval. Okay. So if you have that, then we have the following statements here. This is what the statement means. Then we can say that the series converges if and only if the improper integral converges. This is the test. So this is about what? This is going to converge. Your series converges here. Okay, now what this statement is here, if you guys don't know, this is an equivalent statement. It's also called a biconditional. You say, what's a biconditional? It's a two-way conditional. Biconditional is when you have P arrow Q and Q arrow P. It goes both ways, okay? And it's valid, by the way. Okay, so this is all a part of your integral test. You just have to know that the function has to be positive and decreasing. It's a very specific test. You can't apply it to everything you see. But this is really what this conditional means here. It means the following, okay? It means two things. This biconditional. So let me put that in purple. Even though I like doing my algebra in purple, let's keep it as black there, I guess. So here's, in other words, what does this statement mean? It means if my improper integral converges, then the series converges. Okay? That is the test. If the improper integral converges, then the series converges. That's the first situation. The second situation is going to be if the series diverges, right? Sorry, if your improper integral diverges, then the series diverges. So this is the real meaning behind that if and only if biconditional statement here, meaning that conditional goes both ways. And of course, if it goes both ways, you got the contrapositives for both. At the end of the day, this is really what they're saying. All right? So it's all based on whether or not your improper integrals what? Converge or diverge. Okay, you guys okay with that? It's based on whether the improper integrals converge or diverge. So you might say, what's a good example of this? Well, okay. As an example, the first example is we take the harmonic series here. Now, what do we know about that harmonic series, right? This is the AN. It's 1 over n. But then we look at the function f of x is 1 over x. In other words, we change the variable from the domain being natural numbers to now real numbers. And remember how this works, right? The first term is 1. N is 1. In other words, this is the function. And first of all, it is two things. It's positive, right, over the interval 0 to infinity. And it's also what? Decreasing. And you might say, how do I show it's decreasing? Use calculus. It's decreasing over the interval. So you might go, oh, how do we know that? Use calculus. Or you look at the graph and you say, well, what does that graph look like? Right? You guys know the graph of this curve doesn't look like this, and like this. Here's x and here's y. Okay? So because you have those two situations, and your function is continuous, by the way, over that same interval, right? It is continuous. All we got to do now is what? We're going to have to integrate over. We're going to have to do this improper integral. Okay, so does anybody remember that improper integral? How do you do this? Isn't that going to be the limit as t goes to infinity, or integrate 1 to t, 1 over x dx? Is that right? So you might say, okay, is this going to be here? Remember, this is my I of t. So what you guys want to remember, again, is how to do that. That's going to be natural log absolute value of x from 1 to t, natural log absolute value of t minus natural log absolute value of 1. Now I get to get rid of my absolute values here because t and 1 are positive, right? They're positive values. And then this portion here is 0. So this is really the natural log of t. So, ladies and gentlemen, you now apply the limit. You say, what's the limit? Here's your limit, ladies and gentlemen. We know the following. The natural log of t goes to infinity as what? T goes to infinity. What that means is this improper integral what? Diverges. If the improper integral diverges, what does it mean now about the series then? It means the series what? Diverges. So this is just a very simple example of what we call the what? The integral test. Okay, you guys okay with that? Kind of simple example of the integral test. I just want to give you guys this here. Okay, let me give you guys another example. I think this could even be in your book. I'm not sure. Let me double check. There's a lot of variations of this here. How about this? Let's give you another example of here you may like. Summation 1 to infinity 1 over n squared plus 1 here. Okay, I'm just doing a little multitasking. Okay, so you might say, okay, what about this situation here? Well, I want you guys to know this is going to be your what? Your AN, where AN now, I guess I'll put it down here, is going to be 1 over n squared plus 1. So let's consider the function. You say, what's your function going to be? 1 over x squared plus 1 here. Now, what do you guys know about this curve? F is also what? Decreasing over that interval, like from 0 to infinity. I think I forgot to put the interval there, but anyway. And it's also positive, and it's continuous. Now, if you said, how do I know about this situation? You're going to use calculus 1. All right, you show that it's decreasing over the interval from 0 to infinity. And I forgot, I think I have to label this interval here. This has to be from 0 to infinity. Oh, I did. Okay. Whatever, I did put it. Okay, good. Now, what do you guys think you really have to do here, right? You're going to integrate from 1 to infinity. 1 over x squared plus 1 dx. You're gonna look at the improper integral. So, you know, sometimes students say, hey, you know what? Is this final comprehensive? And I'll say, yeah. Notice we have to go back to what? Improper integrals. Limit. T goes to infinity, 1 to t. 1 over x squared plus 1 dx. What is this going to be? Do you guys know that? What that integral is? This I of t is? What's this integral? Isn't that the inverse tangent? Evaluated from 1 to t? Which is going to equal inverse tangent of t minus inverse tangent of 1. Right? Which is going to be your inverse tangent of t minus pi over 4, because that's inverse tangent of 1. Here's your I of t. So here's the story here, right? As t gets big, where does that I of t go to? Do you guys know? What's that limit, right? Because this is really going to be the limit as t goes to infinity of inverse tangent of t minus pi over 4. What do you get there? What is it? Well, it doesn't this portion here, because it's a limit of a difference, right? Limit of a difference is difference of limits. And doesn't this go to pi over 2? Pi over 2 minus pi over 4. And you go, oh, let me do some algebra, right? So you get what? 2 pi over 4. So anyway, this is pi over 4. So what we showed is that the improper integral converges. That's what we've shown here. Okay, you guys okay with that? Because that's a finite value, pi over 4. What does that mean about your series then? This means the series also what? This is converges, and we like to say by the integral test. So this is a test for convergence here. Okay, you guys okay with that? All right, pretty good. And then I think personally, I'm going to give you guys this important fact that we're going to use. Okay. Let me give you guys a definition here. Definition of what we call a P-series. This is a P-series. Okay, so we're going to call that, this is known as a P-series, just so you guys know. And I guess if you said, what does a P-series kind of look like? Let's look at the terms. Okay, the terms of a P-series start with n as 1. That's like 1 over 1 to the P, plus 1 over 2 to the P, 1 over 3 to the P here. Goes on forever. And then the question's really going to be now, this is the definition of what we call a P-series. So the question's going to be here now, for what P? What values of P do we have convergence? Because we'll look at a whole bunch of different P-series to determine convergence. Okay, so for what P do we have convergence now? Now, okay, here's what this does. Here's what this means. Essentially, you're going to use the integral test. Okay, we're going to use that integral test on this. In other words, we have to determine from 1 to infinity 1 over x to the p, right? We have to see for what P do we have convergence. Okay, so that's kind of the exercise here. I think for me, when I see this section of integral tests, there's things that stand out to me. The essence of it is to show the harmonic series diverges, which I just did, show you an example of where it converges, and then give you the P-series information, because that's going to be the most useful part of the section, 12.3, P-series. And so to kind of express this to you guys, just as a note, and here's something you guys want to kind of note what we're asking. You know, does this series converge? 1 over n squared, right? 1 over n to the 1/2, 1 over n to the 3/2. This is kind of what we're really interested in learning about. When do these series converge? Okay, so we're trying to kind of look at that. Hey, for what values of P do we have convergence here? Okay, these are all the values of P, by the way. Maybe use a different color. Maybe pink. Pretty in pink. Okay, so when do we have convergence? It's going to be really down to this integral test here. And I think we did this before. Did we do this before? You guys know? Anybody remember? Did we do this one? I think we may have. So I want you guys to note something here, right? If p equals 1, then we have 1 to infinity is 1 over x dx. We know we have divergence here. Okay, because we already showed that one. That's a harmonic series. Well, not the harmonic series, but we actually integrated that, right? I think we did. Yeah, Anthony, we did do it. Yeah, we did do it. It's a very famous fact. If I go back to improper integrals, we're going to see it under the improper integral fact. Yeah. So essentially, what you do is you take it by cases. Here's case 1, and then you look at this improper integral here. 1 over, well, they write it, I think, as, what is that? Yeah. This is p not equal to 1 now. And let me do this here. Let me get you guys, see if you guys remind you guys of how that went. That when you did the improper integral, we're looking at this portion here. Yeah, Anthony, we did do that. You're absolutely right. I think when you get p is bigger than 1, the improper integral converged. When p is smaller than 1, that improper integral diverged. Let me double check. P is bigger than 1, yes, we get convergence. When p is less than 1, we got divergence. This was in our improper integral notes. So we proved that in the past. Okay, so we proved that. Now, you might say, well, why do we care about this now? Because now what that means is, here's what that's going to mean for us. Okay. What do we know? Okay. That the series, the p series now, converges for p bigger than 1. Okay? Because that's in your notes. We actually did this. We looked at cases. P is bigger than 1, that improper integral converged. P is smaller than 1, it diverges. When p equals 1, it diverges. So, you know, this is from the past, work on improper integral. And we get to use that now. Now we get to use this. You say, how do I get to use this? Well, if I said to you, what happens with 1 over n squared now? Right? Does it converge or diverge? All you got to do is look at your what? P-value. Is that p-value bigger than 1? What do you guys say? Yes. What does that mean? Converges. Okay. What about this? What if it's 3/2? What does that mean? Converges. This is a convergent p-series. What about this? You say, what if I had 1 over the square root of n? Well, isn't this going to equal what? 1 over n to the 1/2. What do you guys know about this here? What does that say? This what? Huh? Yeah, it's smaller than 1, so it diverges. So this is known as a, convergent. We want to use this language. A convergent p-series. These two. And this over here is known as a what? A divergent what? P-series. Okay, so P is greater than 1. We know that that converges. And that just comes back to this improper integral work we did in the past. I think there's a video on it if you guys want to go back and review it. But that's kind of the big deal of this section here. They introduced you guys what is known as a P-series. And then you have to talk about whether it converges or diverges. Here's another example, right? If they give you 1 over the cube root of n now from 1 to infinity. What do we know by properties of exponentials? 1 to infinity. This is going to be 1 over n to the what? 1/3. What do you guys know about that power? Is that power bigger than 1? No. So this what? Diverges. This is a divergent P-series. Because the power is smaller than 1. It's not bigger than 1. This is strictly bigger than 1. It can't equal 1. It can't be smaller if it's a P-series. So this is known as a divergent P-series. And what would you guys say about this one here if I said to you, okay, what if they gave you this? Cube root of n squared. It's also divergent P-series. You go, well, how do I know that's a divergent P-series? Well, write it down as what? That 1 over n to the 2/3, and now, is it 2/3? Yeah, it's 2/3, isn't that right? So what does that mean? Diverges. It's a divergent P-series. What if they give you 1 over n to the 2/5, ladies and gentlemen? What do you guys know about this power now? Is that convergent or divergent? This what? Diverges. Isn't the power smaller than 1? One over n to the 5/2. What is this? It's a convergent P-series. Is that right? Because your power is what? Bigger than 1. And then sometimes they kind of get a little cute, I think, on you. And they say, what if they give you 1 over n to the 1.02 power? Yeah, the power is bigger than 1. So what do you say? That's a convergent P-series. Oh. No, they don't really. But, you know, what would happen if you said, okay, what if they give you -1, right? 1 over n to the -1. Well, what would happen is a couple of things here. That's really this particular series here. You guys okay with that? Now, you would not use, I'm going to say this to you guys. You see that series? Because the question is, what if they gave you the power of -1? They're not going to. But if they did, here's what I want to remark. You can't use the what? Integral test. So you can't use the integral test here. Do you guys know why you can't? Well, isn't an is n, which will mean that's like saying this is your fn, right? which means f of x is what? X. It's increasing. Yeah, that's the problem. That's the problem, is they won't do that because this function would be now what? It's an increasing function. Yes, it's nice and positive and continuous. Okay. It is continuous, but the problem is it's increasing. The integral test requires you to what? To be decreasing. Way up here. Wherever it was at, wherever we wrote it, okay, we got to be a what? Decreasing function. And sometimes what you got to do is you got to use calculus. So they need it to be decreasing. So they won't do that, but then you say, but Mr. Judge, what if I thought about this and I want to know whether this actually what? Converges or diverges here, right? Do you guys know what you can do here with this one? Yes. Test for divergence. You go, what? Where does an go to as n gets big? Doesn't this go to infinity? Is that true? You guys know what I'm saying? Right? What am I saying? The limit here of an, which is the limit of n equals what? Infinity. This is n gets big. Is that right? Do you guys remember that statement I said to you guys? If the limit of an is not 0 or does not exist, then what do we know? The series diverges. This is the very, 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 very famous test for divergence. Now you say, what does this mean does not exist? Well, we're saying infinity or even minus infinity, so you guys know. That includes infinity and not infinity. And you'll see that in our future. But because this is infinite, it's not 0, we can say that this series diverges by the what? Divergence test. Okay, you guys okay with this? Yeah. If you put what? Where? Mean this? Negative 1 over n? Well, that'll make it... Yeah, I don't know. I'll have to take a look at all that. Yeah. And then I want to kind of give you this other remark too here, just so you guys know. This is a big remark too of the section, right? Here's a big remark. Okay. This is a test for convergence and divergence here. Okay. Now, the book is going to say this to you. That this series is not the same as this integral. Okay, they are not the same. They are not equal. Yeah, I mean, so if I go back to show you guys this, right? Because remember what we did earlier, right? We found that this particular series, right, converges. And you say, why? Well, the integral, the improper integral, that equals what? Pi over 4. So what they're saying to you is this. Just because you find convergence does not mean that this equals the sum. Okay? It's not the sum. So I want you guys to really know that, because you're now entering into an area where all you can do is find convergence, not even the sum. All right? I'm going to say that again. That is not the sum. That's not the area under the curve when you add, this is area under the curve. But this is not area under the curve. They're not the same ideas. Oops, what happened? Where did I go? Series. Oh, what did I do? Integral test, I think. Yeah, there we go. So I just want you guys to be aware that just because you found the area under the curve, that's not the infinite sum. That's not what it adds up to. Yeah. Well, I mean, the series is not continuous, right? It's just a finite list of values. But the proof, if I said to you, what's the proof under the hood of the integral test? The proof under the hood of the integral test goes way beyond the scope of our course. So really, a lot of the proofs that you guys see here for this chapter from here on in, if not a lot of them, or if not all, goes way beyond the scope of the course. Now you might say, well, when do you actually study this stuff and prove it? Well, there's another class you get to take called Advanced Calculus. And you go, what? Yes, Advanced Calculus. You go, well, what is Advanced Calculus? Well, that's when you go back and you get to prove Calculus 1, 2, and 3. You dive deep into the proof aspect of it. So here, you could just give people the tests and what they mean, and then later on, if they major in math and take these courses, well, then you'll study the proofs behind it, and then some of those proofs even then go beyond the scope of a bachelor's degree. Some of those proofs go to like a graduate degree. So the integral test is kind of one of those things too, but they want you to just know that just because you find a sum, just because you find convergence doesn't mean you found the sum. And that's where you're headed to, where a lot of these things, you can show convergence, but you can't show what the sum is. That's other topics you got to take to try to do that. Other advanced math topics to do that. And there are other classes you take that can do that. But there's a lot more math behind it. And that's what you study in the future. So you might even study, for example, what's this sum, right? There is a way to find the sum. We know it converges. It's a convergent p-series, but what is the sum? There's other ways you can go explore that. And in fact, it gets very difficult to find the sums very quickly, where all you can show is that sequence of partial sums converge. That's under the hood. That limit as Sn goes to S as n gets big, that's always under the hood for all these tests. And all you can show is the convergence, though, but you can't necessarily show what the sum is. So I just want to throw that out, And then they might even give you an example like this. Okay, so if you said, what if they give me 1 plus 1 over 2 square root of 2, 1 over 3 square root of 3, 4 square root of 4, And you have to show whether it converges or not, right? If you look closely, this is when n is 1, and this is when n is 2, right? This is n is 3. What is this? N is 4. So this is n square root of n. So that, what does that become? Isn't that 1 over n to the what? 3/2? By some algebra? So this is 1 over n now to the 3/2. What do you guys know about that? It's bigger than 1. This is a convergent p-series. Right? You can have 1 over 3n plus 2, 1 to infinity. Okay, so this is your an, and an will be 1 over this 3n plus 2. So you're going to look at the improper integral. This is that fn. Your domain is natural numbers. So you look at this 3x plus 2 dx. Now, I didn't say this to you guys, but f of x, you say, what is f of x? That's 1 over 3x plus 2. This here is going to be positive over the interval from 0 to infinity, by the way. And this is going to be decreasing. And it's continuous. Right? And you might say, how do I know? Because you get to use calculus. Excuse me. Sorry about that. Okay. Okay, so you say, well, how do I know? Calculus 1. First derivative is positive. All right. So the definition is the limit as t goes to infinity, 1 to t, 1 over 3x plus 2 dx, right? Excuse me. So what do you guys know about this? What's that integral going to be? Do you guys know? Isn't that going to be what? 1/3 natural log absolute value of 3x plus 2, I think. And you evaluate this from 1 to what, t? Is that right? Natural log of 5. Double check. Is that what you guys have here? So what do you guys know about I of t, right? I of t goes to what as t goes to infinity? Doesn't this also go to infinity? So that means this integral what? Diverges. Okay. And so that means the series diverges by the integral test. Yeah. No, because this is not a P series, right? This series you see here is not a P series. A P series is a series that looks like this here. Any series that looks like this is called a P series. Yeah, one variable. And so they can give you another right? So you say, okay, well, isn't this going to be, though? It's the same as if I said to you, right, that's n squared over e to the what? N cubed, by the way. So what you'd want to do is you'd want to look at this particular function, you know, x squared e to the minus x cubed. Let me try to share with you guys something in Desmos so you guys can see it, right? Now, this is the function. Isn't that decreasing starting really before 1? Right? You say, no, that's increasing from 0 to what? 0 to some value, whatever it is right up here, 0 to 0.874, right? But what you need, in all honesty, you don't need it from 0 to infinity. You need it from 1 to infinity. And even if you didn't have that, there's a way around it. I can express to you guys what's going on there. So if you notice, starting at 1, or actually starting at 0.874, you have a decreasing function. That's good enough. Doesn't have to be 0. Okay, so you can now say starting at 1, this is why it's okay. This is still okay. So you have to start there at 1. I can share with you guys another example, and I could just do something like this. I can share with you guys, yes, that's the limit as what? T goes to infinity. Let me do it in purple so I can be consistent. And you guys know how to integrate this? What would you do to integrate this? You'd have to use what? Nope. U sub. Nope. U sub. Let this be U. Okay, because then that means what's du dx? That'll be what? A minus 3x squared, where your dx will be du over minus 3x squared. Okay, so that integral from 1 to t x squared e now, e to the u, and this would be du over minus what? 3x squared. Okay. 1 to t, and don't forget that minus 1/3 du here. Now, here's what I'm going to do here. Okay. Because you get to pull out that 1/3 constant. So this is going to equal, in terms of u, negative 1/3 e to the u, but then we have to know what was u to begin with, right? Minus x to the third. So now I can put back my limits 1 to t. And so that integral is going to be minus 1/3 e to the minus t cubed minus negative 1/3 e to the minus 1 cubed, which will really be 1 over 3e, I believe, minus 1/3 e to the minus t cubed. So double check to see if this is okay, my arithmetic here. Okay, now this is that I of t. So if we say as t gets big, I of t goes to 1 over 3 to the e. That's finite. So you have convergence for the improper integral, which means we have convergence by the integral test. So I kind of just want to share that with you because, you know, this idea, if you said, I want you guys to know, this idea I just started to talk about with you, if you even had like the series here, 1 to infinity, right? Let me double check here. Yeah, what if you have x squared over this x cubed plus 1, okay? This is the an. So this function, if we look at that in terms of x, I'm going to say this to you guys in Desmos, y equals x squared divided by x raised to the third power, right? Plus 1. Okay, let's get rid of this curve. It's a kind of a similar thing here. You got to be careful here. Okay, you might say, Mr. Judge, what's the deal on this one? Because after 1, you're decreasing. You guys see what I'm saying? So if they gave you this, you say, but the problem is, right, from 2 to infinity, the function you'll be looking at for the integral test is this function. This is what? Decreasing over that particular what? Interval. And it's positive and it's continuous. But what's the problem? They told you to start where? They told you to start at 1. You guys okay with that? But the function doesn't satisfy the hypothesis. You want it to be strictly decreasing over that interval, and it isn't. Because you're looking at this function in Desmos. You go, oh my God, that function starts at 1.26. It doesn't start at 1. And then you say, well, what do I do, right? Well, very simply, you kind of fix this. You say, what do you mean? Well, if I use, and I apologize to you guys, that should be an n, okay? I was jumping ahead of myself when I used the x. So you can fix this very easily. You say, how do I fix it? Well, isn't it true that that series is equal to the following? If I say 1 squared over 1 cubed plus 1, isn't that when n is 1? Now start at n is what? 2. So this is really, looks like it's 1/2. That happens when n is 1. And you go from 2 to infinity. N squared, n cubed plus 1. So what you would do now is this. You can now apply the what? The integral test. But you're going to integrate now from 2 to infinity. N squared over what? I'm sorry, not n. Now we can put the x. Okay, just to kind of throw that out there for you. And yeah, you can show by calculus that this thing is what? Decreasing from the interval now from what? What's the interval now? Not at that 1.26, but starting at 2. So you're saying, okay, starting at 2, I don't think I could put the point there. But starting at 2 to infinity, yes, that's decreasing. It's positive. Okay, you guys okay with that? You guys see the point? So you must satisfy the hypothesis to use that integral test. And then now, just so you guys know, if this integral, by the way, this thing is infinity. This diverges. So because this diverges, the whole thing what? Diverges. Doesn't matter if you have that sum of 1/2 plus a divergent series, because that's like saying this sum blows up to infinity, right? Believe it or not, the sum blows up to infinity. So infinity plus 1/2 is still infinity. It's still a divergent situation. So this is, this is something that shows up as well. Okay, diverges. But I do want to mention too, just so I'm on this to let you guys know, if I go to the browser again, I go to my website. You guys aren't in statistics. You guys are in calculus 2. So if I go to the website over here, ladies and gentlemen, you have wealth of resources here. If you want extra examples, right? I'm going to double check too if I have more. I think I may, but let's go back. There should be integral test examples. I'm going to have to find them. Okay, so when I get home, I'm going to put a note in my phone, look for integral test examples, some further examples, and I could let you guys see some of those if you like. Shouldn't be too hard to find, but I believe I have some. And so in your homework, an assignment, you have some questions here on 12.3, which is integral test. Now I'll check at home to see if I have more examples for you guys. So you definitely want to work on some of your series here because, like I said, starting on Monday, we're going to look at the limit comparison test and the comparison test, and then it's alternating series and some others. And so, there's just various tests that we can look at, and I do have, like I said, additional examples. So anyway, all right, looks like we're good to go. I hope you guys enjoyed the lecture, especially you guys at home. Thank you, Anthony, for verifying some information. I think that's great. So we'll see you guys later. Have a good weekend. I don't have office hours today because I'm going to have a medical procedure I got to get to in a meeting too. So anyway, I got to get out here early because of the medical procedure. And I think I'm having somebody meet with me around noon. So I'll see you guys later.